What's up, clovers? GM. Welcome to today's video where we're going to discuss the ERC-721A, the Azuki's spin on ERC-721 contract by OZ, the Open Zeppelin Collective, I guess. This has been one of the most requested videos in my Discord channel. Here we are making this video. I hope you're excited as much as I am. We are going to basically go through the literature that is present for ERC-721A, and I'll show you a live example of a project which has used ERC-721A and link to it in the description and everything so that you can copy the code and walk you through exactly why does ERC-721A reduce the minting gas cost. But before we get started, please make sure to hit that like button, subscribe to the channel if you're new here. If you have any questions, please let me know in the comments. I try to answer wherever I can. And if you're looking for some serious help, hop on to my Discord server. There are a bunch of others who are helping each other out. And sometimes I also try to chime in over there. And with that, let's get started. So first, if we go through the blog post that Azuki had published announcing the ERC-721A, which is basically an improvement on the ERC-721 implementation. The TLDR is very simple, but the main thing that you need to understand is it helps you reduce minting costs for more than one mint. So if somebody is trying to mint from your smart contract, and they're trying to mint, let's say, more than one NFT in a single transaction, ERC-721A sort of reduces the amount of gas they need to pay compared to ERC-721 enumerable, which is an extension of ERC-721 by Open Zeppelin. It's something not very difficult to understand, but this is something that, which sort of catches our eye, which is they have shown the measurements, and according to them, if somebody is just minting one, they stand to save 78,000 units of gas. Now remember, one gas multiplied by the gas rate, which is generally 20 to 30 GUI these days, is the amount of total gas in ether the user ends up paying. So 78,000 at, let's say, even 30 GUI is a very significant savings. But if somebody ends up minting 5, they end up saving 531,000 units of gas, which is huge. Of course, their assumption is 300 GUI, which is not the case these days. These days, the average is more like 50 to 70 GUI. But anyway, the difference is, not that big, but still decent enough for you to consider using this. And how does it all work? Basically, they've made a few optimizations and taken some assumptions which ERC-721 enumerable does not. First assumption that they take is that minting will be done serially. So 0, 1, 2, 3, 4, 5. If let's say 500 have been minted, the next person will mint 501. ERC-721 enumerable basically lets us say that this is the token ID that the user is trying to mint. And that way what happens is they have to store each and every one. Whereas in the case of Azuki, what they've cleverly done is just store the first token ID of the mint. So let's say there have been 500 mints till now, and I'm minting 10. So what they will do is they will assign me the 501st token, and they will increase their total count to 510. So if somebody is looking for owner of 505, the mapping will return nil. So they will look for 504, then 503, 2, and then suddenly at 501 they will find me and return as the correct owner. Now let's say I have minted from 501 to 510. So you know that 501 is filled, but 502 to 510 is empty. Now the next user who comes and tries to mint, they will mint at 511. So they will put their owner address at 511. And let's say if they're also minting 10, they will also leave 512, 13 up to 520 empty. But the total supply would be increased to 520. So when the smart contract is trying to figure out the owner of, let's say, 518, 14, whatever, they will just go back until they find an owner. And that's a very clever hack to sort of reduce the gas fees. Their assumption is that, people don't really need to have optimized reads because, you don't really end up paying for reads. So they have pushed a lot of processing to the read, but not enough to the write, which is a trade-off that you might or might not want to take. Another thing that they have done is that because they get the number of mints directly in the parameters, they directly save it to the user's balance on that smart contract. in OpenZeppelin, what happens is every time there's a mint, the balance is updated by 1. So you run a for loop in OpenZeppelin's smart contract, and for each for loop you end up paying gas for 1 by 1 increasing the value. And the third optimization is what I've already sort of explained, but yeah, this basically they have owner number 100 is Alice, so 101 is not set, 102 is not set, then 103 is Bob, and 104 is not set. So at number 104, it means that the total supply is 105, because in ERC721A, as of this recording, the tokens start from 0, not 1. So when you're looking for the token URI or the owner of, let's say, token ID 104, first we will check whether the token that we are trying to find, is it less than the total supply. If it is, only then we will say that there is some token URI and we go and find it. But if it is more than or equal to the total supply, then we say that it's not minted yet. And that specific logic you can see in the code over here. Let me just increase the size. It says owner of the token ID, and then it says require exists token ID. So in the exists, it basically checks that token ID is less than the total supply. And then basically it creates a variable lowest to check, and it creates a token ID minus the batch size plus 1. The maximum batch size is the total number of tokens I believe the person can mint at once. And then they generate a for loop which decreases the current value, the current index, and figures out if the owner is available. So it checks if the owner is not equal to address of 0, which means it is something which has been set, then in that case it returns the owner. Of course, this is an old block, and in the newer ones, there's an ability to burn. So in that case, they also store a mapping of burned. They make sure that the index is not burned, because in the case of burning, you basically send it to address 0 at times or remove it from the mapping. But if something is not present in the mapping, how will you remove it? So yeah, this is basically how ERC721A reduces the gas for multiple mints. It might not reduce the gas for single mint if you're not using the ERC721 enumerable when using the OpenZeppelin code or the OpenZeppelin wizard. If you want to check out the code, it's available at Chiu Labs on GitHub. The repo name is ERC721A, and there in the contracts folder you will find ERC721A.sol. This is the file that you need to sort of import in your smart contract to be able to use it. You can of course go through the code and make sure what's happening. I can probably do a deep dive of the code later on. If this is something that you want me to go through, please come into my Discord, let me know, let the other people know that this is something that is valuable, and I will do it. This is a new project that I've found, which is called Inverted Muffers, and they have sort of used the ERC721A. And I opened their contract, and this is something that I thought is very simple for the rest of the community to be able to use. So what I'm going to do is I'll link to their Etherscan in the website in the description, so you can go through it. But what you need to do is, once you open the website, just open the invertedmuffers.sol and copy the whole file. Then you go to remix. Once the remix is open, just right click on contracts, click on new file, and write whatever the name of your contract you want to be, right? And then you basically paste the code that we have just copied earlier. Some of you told me that there is a problem with my font size, so let me just increase it. So now you can see that they have a max mints over here, which is set to 69. Nice. They have a max supply which is set to 10021. I guess this is the max supply for muffers. Then they have a mint rate which is again 0069. Nice. And they have a base URI that is used for generating the token URI, right? So these are the things that you also should sort of put down. Now they are inheriting from ERC721A, which was imported using ERC721A/contract/ERC721A.sol. What Remix does is it searches for this on npm. So ERC721A is an npm module. It's present on the npm registry. So this is how you import the ERC721A. Ownable is also something that has been imported, and then the inverted buffers are inheriting from ERC721A. These are the variables that I just walked you through are the variables that have been set. They are not related to ERC721A. This is just something that is there for you to add restrictions or functionality to your smart contract. In the constructor, you just call ERC721A with the name and symbol. This is very similar to ERC721. The Open Zeppelin's ERC721. Now, before I move to the mint function, I'll also walk you through the other functions that are there. So withdraw is a function that is present, which basically helps you withdraw the ether that was sent to that smart contract. So this is something that I recommend you add as well. There is a non-reentrancy guard that also that you should add, but it's not really that important if you are sort of just bringing it to the owner itself. And then a couple of other methods. One is the underscore base URI internal override method. So what this method does is, if you open the ERC721A and search for token URI, you will see that the URI is created by base URI, which is figured out by calling the base URI method, this underscore base URI method, which returns an empty string. But since we have overridden this, we are returning a base URI that is available here. Another thing that you might want to add if you want to add reveal and everything is set base URI method, so that you can change the base URI. I've explained this in my video where I explain how to reveal stuff. So yeah, this underscore base URI method is called by token URI over here. And then what it does is with the base URI, what was returned, this is where they append the token ID after it. What ends up happening is whatever this value is, let's say this value is this, so, and the token URI, let's say 35, so they put 35 over here and they just make this call. They just try to get this from IPFS. So this was the base URI, and then there's a function to set mint rate, which can basically change this mint rate value. All right, so these are the supporting functions, but the main function that you're looking for is the mint function, and this is here. It's here. Now this project, there is no, I don't see any whitelist over here. I just see that it's there. Anybody can mint up to 69 in one transaction for one wallet basically, and the total supply is 10021. It's a pretty simple standard smart contract. So before this safe mint is called, there are 3 require statements that are there. So the first statement is quantity, the amount of tokens that are being minted, plus the number of tokens minted, number minted by message.sender should be less than or equal to the max mints, which are 69 over here. So where does this number minted method come from? So I copy this and I go to GitHub and I command F and paste it. And you see the method is over here. Let me increase the font for you. This basically stores the address data for the owner and number minted. So when we are safe minting, what happens is whatever the amount is here, let's say the initial value will be 0 and you're minting 10. So this number is increased by 10, and then you mint, let's say again, and you mint 10. So this number is again minted by 10. So the number minted sort of returns how many tokens have been minted by this specific user. So very helpful method for you, especially if you're using ERC721A. All right, so if this is greater than let's say 69, we just respond, or max mints actually, we respond with we throw an error with the message exceeded the limit. The next thing that we check is the total supply. What is the total supply that has already been minted plus the quantity which we are going to mint? Those basically should be less than or equal to, the sum should be less than or equal to the max supply, right? And the total supply is very common. I don't think this is something that I need to explain, but what it basically does is it sort of returns how many have been minted. So it currently has current index minus the burn counter, because as I was saying, there's a burn mechanism also, and we subtract the start token ID, which I believe is 0. Yep, it is 0. So I guess if we can just change it to 1, this is something that could help you start the ERC721A with the index 1. But anyway, the total supply is the method returns with the number of NFTs that are currently available, currently minted or available or live. So yeah, the sum of total supply plus the quantity that is being minted should be less than equal to the max supply. Otherwise, the error is not enough tokens left. And the third thing is message.value. Value is the amount of ether that is sent, should be greater than equal to mint rate into quantity. So quantity into mint rate. Otherwise it throws an error with not enough ether sent. By the way, when I say ether, I mean the chain's primary token. So for Polygon or Matic, that will be Matic. For BNB chain, it will be BNB. Any EVM based chain which is like Ether or BNB or Polygon, the native token is basically what is sent in the message.value. And when we write ether over here, it means multiply this number by 10 to the power 18. So a bunch of you have also asked me that, will it work on Polygon, will it work on BNB? And my answer is yes, because this will work on any EVM based chain. When we write ether over here, it doesn't mean Ethereum's ether. And then once everything is cleared, what we do is we call the underscore safe mint method, which accepts two arguments. The first is who do we generate this mint for, and the second is the quantity, the number of tokens that we have to send. Alright, so this is basically how you generate an ERC-71A compatible smart contract. Now what you can do is just go ahead, compile it, and once the compilation is done, you go there and you before this, what I want to do is make some simpler choices, because 6910, like these numbers are multiplied, they are not something that I just want to live with. So I'm going to change it to 1 Finny, the ether, the mint rate, and I'm going to change the maximum mints to 100. All right, and I'm going to compile it again and deploy it again. Oops, I deployed the wrong contract. Make sure you selected inverted muffers or whatever is the name of the contract, and you deploy that, and you can see that the gas cost has sort of changed. Great. And then there's a mint button present over here. So now first what I'm going to do is I'm going to send one Finny, and that will be the quantity that I'm going to mint. So I'm sending 0.001 ether to mint 1. All right, and I click on transact. The transaction goes through. You can check out the gas cost that was required. So I've basically copy pasted the value over here. For minting 1, we required 101,604 gas. Now let me mint 2, and for 2 I need to send 2 Finny, and I click on transact, and now you can see the gas cost was even lower. Now why was it? Because whenever you're minting for the first time, there are some things that are initialized, and that sort of requires more gas. But if I mint 1 once again, this time you'll see that the gas cost that was required is much lower than the first gas cost that was needed. All right, but as you can see, for minting 1 and minting 2, the gas cost difference was not very different. It wasn't a lot. Now let's say I want to mint 10, and I press 10 over here, and I press transact. This time if you check out the gas cost for minting 10, the value is 85071. Great. So this is on the Azuki side of things. Now what I want to do is I want to open the OpenZeppelin wizard, and what we're going to do is we are going to create an enumerable auto increment ID and all those things, NFT, right? And then we are going to open this in Remix, or I can just copy it and generate a new file over here, enumerable. Great. So now that I have that enumerable SOL, first what I'm going to do is I'm going to copy these values. Great. Now that I have all these, and I can get the U/56 quantity present over here. Then what I do is I add a require and the safe mint and everything. The only problem is the number minted is not available, so I'm just going to remove it for now. Let us assume anybody can mint whatever they want. But yeah, so the it's not going to be complete apples to apples in this case, but this is something still that we can figure out what's going on. All right, and here what we need is a token ID. We can't have the quantity being sent over here. So once the require statements are good enough, like they don't need to worry about the require statements. Once the token ID is available, what we will end up doing is, and let's say I++, and let's say we are starting from 0 in this case as well. So I want to optimize this a bit. So rather than this, what I'm going to do is, actually this should be token index equals to 0, and I'm going to do safe mint. And once everything is done, what you do is you add the token index with the value of quantity. So at 0 the token index will be 0, and let's say we mint 1, so the quantity will be 1, so the 0th will be minted, and then we move forward. And because the quantity was 1, the token index will be 1. All right, so this token index is the forward looking token index rather than the backward looking. And we run this, compile this, and then there's already an error. All right, this I need to make it payable and remove the only owner. And I think this one was external, correct? So I'm going to make this external as well. All right, now we compile, and the compilation works. I kind of deploy it, and this is the my token over here. You can see the method is very similar actually. Now the amount of fini that I have to send for 1 is 1, and I'm going to transact. The transaction goes through, and you can already see the amount of gas that was required. Now this one was for ERC721A. Now this one will be for ERC721 numerable. For minting 1, the gas for the first time was this. All right, now let's mint 2, because that's what we had done earlier as well. We need to send 2 fini for that. And once we do that, the gas cost is, you can already see that it's nearly double of the first one. And if you compare it with this is, I don't know, the difference is huge. And let's say we mint 1 again, just to make sure that the value was not changed because of the first initialization of stuff. And lo and behold, we end up paying more gas. And then for minting 10, safe mint 10, and I transact again, the value works, and the gas that I end up paying is this, which is humongous. The gas that I paid was 1.198 million. This was 85,000. So you can see the difference, that the difference is just huge. So if you're looking to be cheaper on the mint day, make sure that you can actually figure out how to use ERC721A. Thank you so much for watching the video. I hope this was something which was helpful for you. If you like this video, please make sure to hit that like button, subscribe to the channel. If you have any questions, leave in the comments, and please come on the Discord channel. There's Discord server actually, and there's a bunch of other people who are helping each other out. You can either ask questions or answer the others. It's generally very nice atmosphere, I would say, over there. So yeah, come on over there. I hope to see you again next week. Goodbye.